lesson, we finished at making polymers. And so if we had two different amino acids, how are we going to combine them? And we looked at how the amine group of the one amino acid could combine with the carboxyl group of the second amino acid. So if I just go back a bit on here, so there's your amine of the first one combining with the carboxyl group of the second one. And then the OH comes off together with the hydrogen from there. So when polymers combine, you lose water. Or if it's an acyl chloride, okay, an amino acid wouldn't have an acyl chloride, but if this was an acyl chloride, you'd get HCl coming off. Here it's H2O. So, we just we looked at last time how you could work it out. You just had to count your atoms very carefully so that you drew the correct molecules. And then also the carboxyl group on the first one could be attacked by the amine of the second one, and then we'd get a different combination. And that's how your proteins are made, your enzymes, your RNA, your DNA, and I'm sure all those people doing biology know a lot more about it than I do, would be able to explain that in more detail, how the enzymes make the different proteins. Okay, April, you said what do you mean by losing water? Do you notice when these two combine, the C double bond O has an OH here, but it doesn't have it in the condensed product or in the protein. So what has happened is this OH has come off. And if you look over here, this NH2 now becomes NH. So it's lost a hydrogen. So the hydrogen from here, together with the OH from the carboxyl, makes water, HOH. Is that clear? Okay, that's important to know because we're going to now look at the opposite, where we're going to hydrolyze it. Okay, where does it go? Obviously in your body, you're forming your water and your bloodstream takes it away. If you were doing it in the laboratory, that would be part of your workup to get rid of the water afterwards if you just wanted the polymer. That's when you wash your polymers and all that sort of thing. So it just simply goes into the reaction mixture and then you get rid of it later. So in your body gets rid of it by sweating or urine or that sort of thing, or breathing, and in the lab, you work it up and you get rid of it. Okay, right, so that is making polymers, making proteins. So your fabrics are made this way, all the, actually even cottons and so on are all sort of made this way. But when I want to break up my polymer, then instead of losing an H2O for each peptide bond that's being formed, I add in, and that's why it's called hydrolysis. Hydrolysis, water, that sort of thing. Now, if you think right back to the 7 tips when I was talking about reactivity, and we were talking about the leaving group, the better the leaving group, the more reactive. Do you remember that bit? Okay. Now, and we touched on this again, I think, in the last lesson. When we want to break something up, the more neutral the substance, the more likely it'll come off easily. It'll be the better leaving group. So for esters and for amides, they are quite unreactive in neutral conditions. So they won't, they'll still stay combined. But under acidic or under basic conditions, what happens is you turn the leaving group into a neutral compound, and so they break up quite easily under acidic or under basic conditions. So let's have a look. Here's my polymer, could be my polymer for my fabric or your protein or whatever. You know, when your stomach acid starts digesting your food, your proteins, your meat that you've eaten, it pretty much does this. It starts breaking up the proteins into smaller groups. So what you've got here is HCl. The Cl is just the anion of the acid. The important part is the H. And the H2O is important because we're adding water. So where do you think the H is going to add on to? Sorry, that's just acting as a catalyst. But for the H2O, think of H2O as H and OH. So OH, you've got a negative oxygen. Which part is the oxygen going to add on to the OH? This carbonyl or to the nitrogen? Because this peptide bond has to break. The carbonyl, because this carbonyl is slightly positive, the oxygen is more negative, okay, in water. So the O of the water is going to be attracted to the carbonyl, and then the remaining H is going to go and be attracted to this basic nitrogen group with a lone pair. So, as I say, that's going to break. And can you see what has happened? I have, under these acidic conditions, my OH from the water has added on there. My H of here has added on here. Okay. So this has become a positive cation, and this is the anion. So under acidic conditions, I get a fairly neutral substance. Okay, I've broken it up over there. So this is the first amino acid, and this bit over here is the second amino acid. Now this is, okay, so the NH gains H from the H2O and 1 from the HCl. Yeah, that's correct. And that's why you need the acid. So the OH adds onto one of them, and then the H adds into the other one. Yep. We landed up with, why have I got two reds over here? Okay, that's supposed to have been a blue. Okay, sorry, that NH over there is this NH. So one of these is supposed to be a blue. Okay, now, John, you said that why can't it just gain one to be the NH2? A good question. What happens if we just focus on this bit and we ignore this NH2 over here? So we just focus on this bit. The OH goes on here and the NH goes there. And sorry, I should have made this one blue for the NH. And so the H of the OH is here, and the H of the water is here, and the OH from the water is there. However, this is an acidic hydrogen. This is an acidic solution. So of course we got hydrogens being attracted to any base. And remember, your amine group is always basic. So this is a basic part. Weak base in an acidic solution, what is it going to do? It's going to accept a proton. So that's why this H has added on here. This has just become a proton acceptor because it's base, and we're in an acidic solution, so that's why that H is added on. So Caleb, the two black H's over here are those over there. And I'm just showing this as it hasn't been part of this broken bond here, but being in the solution with acid, it's acted as a base. Now over here, I have NH. All right, okay, and I see what I mean. Okay, I can see what I've done here. Sorry, I haven't looked at the slide since last year, so I've suddenly realized that one's supposed to be blue. It has to protonate more because you've got this black one over here is this blue one over there. Okay? Is that clear to everybody? So this black one over there is that blue one. Then what happens, the H from the water adds on, so that's this red H. So I've got NH2, but NH2 is basic, so it's going to donate, and it's going to accept a proton, and that's where this H comes. So can you see, if you like, there's two HCl in front of here. That's the one HCl, and that's the other HCl. So April, nitrogen forms 3 bonds, okay, if it's neutral, but because it's got a lone pair that it's quite happy to share out, it can share it out with something else, but then it gets a positive charge. So whenever you draw 4 bonds on a nitrogen, it has to have a positive. If it's only got 3 bonds, it's neutral. So here I've got 4 bonds. So it's like your ammonia, NH3, and your ammonium ion, NH4+. Okay, so that's really what's happening. This is like ammonia reacting with the HCl. So what we're trying to say is, when you're breaking up, one of these condensation polymers, don't just focus on your peptide link or your ester link. You've also got to consider what else is in this molecule. You've got basic groups in this molecule, and you've got acidic groups in this molecule. Now, the acidic groups don't react with acid, so we can ignore this acidic group, okay? They don't react any further, but your basic groups do. So first break it up by adding your HOH, and then think of, now how is this going to react further in my acidic solution? Does that make sense? Okay, so have I answered now everybody's question? So sorry about this, this is supposed to have been blue, and that H and Cl comes from there, and that H and Cl comes from there, and this hydrogen comes from the water. So Caleb, when you say so there is nothing else, I'm not quite sure what you mean there. Yep, so one H comes from the water. No, there's no other products. So the longer the chain, the more it breaks up. But pretty much we've added HCl and H2O. So for every peptide link, so for every this peptide link over here, we have to add water, HOH. And then the whole mixture is acidified to make the reaction work. If you don't acidify it, if you just take this peptide and you put it into water, it's just going to form, protein doesn't dissolve in water. It's just going to sit around on, in a separate layer. Or if you've got a small enough one, this would dissolve in water because it can form lots of hydrogen bonds. So if you just had something like this, a dipeptide, it would dissolve in water, but it wouldn't actually react because your water isn't strong enough to break that bond. You need to protonate it first. Now, I haven't explained how that hydrogen makes it work. Its mechanisms, and you do that later. It's just under acidic conditions. What really happens? It starts protonating the oxygen over there. If you really wanted to know. So if I've got acidic conditions, it protonates this, makes this a bit more positive, so it attracts the water more readily. Okay, so April, you can multiply the acid to get enough atoms. Yes, because the acid will be in excess. Okay. Caleb, any acid. Okay, so H3O plus just represents an acid. So it could be sulfuric acid, hydrochloric acid. So if it was sulfuric acid, this would be a sulfate. If it was nitric acid, this would be a nitrate. Okay, but you're forming a pretty much a neutral substance over here. I mean, I know that's an acidic group, but generally it's not strongly basic or strongly acidic, and that's why it can form. Now the same thing can happen under bases. Now with bases, remember what I said with an acid, really the way it works, it protonates that oxygen and just makes it more attractive for the water to go to that more positive carbon. Here we actually have a stronger nucleophile. It's much more negative, OH minus. So the OH minus now attacks the carbonyl, okay, breaks that link. So when that link is broken, you're going to form an OH over there. Now you've got water. I mean, I should have perhaps said aqueous after this, because we've still got water around. Okay, so can you see what's happened here? We've got the oxygen from the water, from the OH. Okay, now why have I made it O minus and not OH? Does anybody want to have a it is initially OH because I've added OH, because I've added hydroxide, which means I've now formed this type of thing, okay? That's been formed. But it's now in basic solution. Well, it's not the sodium. Sodium is a spectator ion. That's just any hydroxide would have worked, okay? It's the acid donates a proton. So when I form the carboxyl group, so the OH attacks it forms the COH like this. This is acidic, but of course everything is in a basic solution. So the moment we form that carboxyl group, the COOH, it acts as an acid and promptly donates its proton. So that H gets donated, and so I get just the salt formed. So a good thing to remember is if you're doing an acid or base hydrolysis, you're always going to form a salt. Okay, and then there's your other one. So what happens here? Remember that H that comes off now goes really onto there eventually. Might not be the same one, but it that gets neutralized there. Or you could say the H comes from that one. It's just from the mixture somewhere. So yes, April, almost a second little reaction. So we add the acid and base to give the impetus to break this bond, but then they will react further. In fact, if you did a career in synthetic chemistry where you had to make things, you spend a lot of your time protecting groups, adding things onto your molecule to protect it so it won't react further, and then you do this. So it's not just sort of like mixing two things together and hey presto, getting the stuff you want, because if your molecule has something else in it, it's going to perhaps react with your reaction mixture. So yes, you can get two little reactions going, like the one you want and the one you don't want. So Caleb, there shouldn't be two Na pluses. Well, there would be, because as I say, I'm only showing the organic thing over here. So when my OH adds over there, what happens? This automatically reacts with base as well, and so that H gets extracted and forming water. And so, and then this acts as a base and grabs, hydrogen from the mixture, from the water. So it's sort of, we have these acid-base reactions happening while we're doing the hydrolysis. So see, Caleb is typing. Yeah, okay. Just think of it in two stages. If I do an acid or base hydrolysis, I break the peptide link to form the carboxyl group and the NH2. So do that first. Then when you've done that, then you say, okay, I've now got my two amino acids or two esters or whatever, because you could also break an ester link, so not two esters, my alcohol and my I've gone blank, carboxylic acid. So you've broken it up, but now you've got to consider, as April said, the second little reaction. So then you've got to go, okay, I've got my compounds formed now. Will they react further with the acid or base? You know, if it's acid hydrolysis or base hydrolysis. So if you've done an acid hydrolysis, any basic part of the molecule is going to react with that acid. So any amine that you've got is going to react to form a salt. So it's going to be straightforward. Acid plus base gives salt plus water. Okay, if it wasn't basic hydrolysis, then you look at your molecule and you go, do I have any acidic components in my molecule? So like a carboxylic acid. And if I have any carboxylic acid, it's going to be a acid plus base reaction. So any acidic part is going to react with the base to form a salt. Okay, so I hope that's clear. So whenever you get a hydrolysis of either an ester or an amide, what you need to do is look for the ester link or the amide link, break it up, add the OH, because hydrolysis means you're adding OH and H, add the OH to the carbonyl and the H to the N group or to the O. Okay, right, so can you see that now, Johnny? And when you've done that, then you go, right, if it's in acidic conditions, any base like an amino group is going to react with it. Or if it's under basic conditions, any acidic part is going to react with it. So I think April's said it very clearly there. It's a second little reaction. Okay, but is it clear now? Yeah, okay, right. Okay, so what I'm going to do now is, here's just a thing of, and I said, okay, 2.2 minutes. This is Flint Scientific. It's sort of done for teachers on how we could do demonstrations for you, but seeing I can't do demonstrations, I'm just going to go to, oops, 2.2. Okay, so what he's doing here, he's got nylon. Now, nylon is ester links. I think it's an ester link. So what he's doing now, he's adding acid. And I think you can see as he's adding acid, can you see how it's just breaking apart? Because all the ester links are being broken. It's a hydrolysis reaction. Okay, so just to show how easily the fabrics do break down under acids, and you could have done the same for bases. Then what he does here is, I'm just going to go to 5.2. He now adds acetone, propanone. Okay, notice how the nylon does not react whatsoever, but can you see what's happening to the polystyrene? So the polystyrene is just dissolving, but the nylon isn't. The nylon being in bits and ribbons is sort of falling down, but it's actually not dissolving at all. And that's the difference between the two types of polymers you can get. So remember in level 2, you do what we call the addition polymers. That's where you have alkenes bonding together. So polystyrene is an example of an addition polymer. And polystyrene, you notice when you added the acid, had no effect because it's all non-polar connections. You know, C, single bond C, single bond C, single bond C, until it's one great big enormous polymer. But so there's no place for the acid or the base to attack because there's no slightly negative or slightly positive part. So polystyrene is not affected by acid or base. But if I add a non-polar solvent, can you see what happened? It just dissolved. So addition polymers that you learned about last year are very soluble in non-polar solvents, but are fine under acids and bases. This will affect your properties of plastics, if you want to use it for food grade or so on. You tend to use addition polymers. So I'm just going to have it somewhere over there. Okay. So for your plastics that you use for food, yeah, propanone. Well, propanone is polar, but it doesn't form hydrogen bonds, so it can dissolve non-polar substances. Just like sort of ethanol is got a non-polar part in the methyl group, and it's got the hydrogen bonding part in the OH group. Propanone sort of fits sort of in between. It's only got the temporary dipole and the permanent dipoles, but it can't form hydrogen bonds. So it's not bad at dissolving a lot of non-polar stuff as well, even though it's polar itself. So your nail polish, you know, acetone is what the old-fashioned way of getting rid of your nail polish. Okay, so as I say, you know, the implications for this is in terms of food grade. You wouldn't really use the condensation, so you wouldn't really use, the condensation polymers, your ester links and your peptide links for food grade plastics very much, but they're very useful for biodegradable plastics because they break down more readily. Okay. Right, so Johnny said the smaller molecules, yes, they are more polar, but as I say, I know you sort of learn like dissolves like, so polar will dissolve in polar and non-polar will dissolve in non-polar. It's not quite as straightforward and as clear cut as that. So there is overlap. Okay, just like oxygen, you know, dissolves in water. It has to, because not very much, of course, but it has to. Otherwise, your fish couldn't breathe. But you know, oxygen is non-polar, water is polar. But so it is. You know, it's the degree of how much it can dissolve. Okay, so I've said over here, I think we've answered that. The acid affects the nylon because of that link, but not the polystyrene, because the polystyrene can't get attacked by acids or bases. Okay, so that was just like an extra. Right, here's just checking. If you get given a polymer, you often have to break it down to the monomers, and I find sometimes students can't draw the monomers very easily. So have a look at that. Have I made that top polymer with just molecule A? So is it just repetitions of molecule A? Or is it repetitions of molecule B and, you know, the two parts of molecule B? Or is it the repetition of the two molecules of molecule C, of number C? Who would like to have a go? I've actually got to look at it myself because I haven't done it for a while. C, and I think you are correct there, because I know it's certainly not monomer A. Remember, when you're looking for these things, look for the peptide links. And remember what I said last time, if it's like CON, well, this is COO. If it's COO, 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 it's all in the same molecule. If it's COO, and then it's OCO, and then it's COO, you know, in other words, it's reversing every time, then you know it's the diol with the diacid. And that's, so it's definitely not A, and you've just got to look at this one, and, oh, so there, it's number C. So Caleb, you were correct there. Can you see this bit over here? Is that repetition over there? Okay, and this bit over here, so this carbonyl to the carbonyl has got a methionine and a methyl group. So there it is, carbonyl to a carbonyl with a methylene and a methyl group. So when you get asked to break it down, you know, draw sort of bonds, this bit is always the OH, so simply add an H to the end, and this bit is the diacid. If this was under acidic conditions, you would just simply add OH to each carbonyl and the H to the alcohol. If it was under basic conditions, this is still OH, okay, because alcohols are neutral, remember, they're not amines. Amines will react further, well, with acid alcohol. Alcohols don't. But what, under basic conditions, would my carboxylic acid do? What would I have to add on here? O minus. Correct. Well done. And of course an O minus on there as well. Good. Okay. Right. So, which one does not match this polymer? So we're doing the opposite now. Okay. So again, you focus on all the peptide links and notice, can you see they're all NCO, NCO, NCO? So it's all the same molecule, and I've only given you one in each case. But now you look very carefully. So as I count, there's your carbonyl. Always make your sort of your carbonyl your main thing to look at. So there's your carbonyl, and you've got a methylene, a methylene, and a methyl. So you've got a methylene, and a methyl, and then you've got an amine. So which one would you like to say? Is it A, B, or C? Does anybody want to have a go? Yep. Okay, so there it was just breaking it up. Oh, hang on, B. Why isn't it this? CNH. CH, NH. Oh, sorry. Remember, we're going the opposite. Remember, this one does not match the polymer. That was the question. So yes, B could be used to make the A could be used to make the polymer. B is one that does not match it. Does that make sense? Yes. I fell into the same trap, Caleb. Okay, so well done, John Lee. You're the only one that read the question. Okay, so you could be asked questions in different ways. So, make sure you read the question carefully. I don't think you'd ever get a question exactly like this. This was, I just did so that you try and look for what could be or what not. Remember, of course, your acid chlorides are always useful precursors because they react more quickly than the carboxylic acid. Okay, right. And I hope you can see that A and C are exactly the same compound, except this is the acyl chloride version and this is the carboxylic acid version. Now, that pretty picture is something you would have to get used to and learn. I've got a slightly different reaction scheme given at the back of the booklet, but you're going to need to know something like this because you will be given a reaction scheme in the exam and you've got to work out possible reactions. So it's good to start getting ideas of how they all interlink. Pretty much April, yes. That's why it's good to start now, and that's why I don't ever leave this organic to the end of the year. I can send you a copy. I got this, well, yes, University of York. Okay, I got this off the internet, but can you see this blue is slightly different here, and this blue is slightly different here? I just blanked it out. What I can do is I can send you the PowerPoint, and then you've got it there. And then you've actually got all the links as well if you wanted to watch the different things. So would you like me to send the PowerPoint? Okay, right. I don't know if I can load a PowerPoint up in Ottle, so I might just actually, with my next email, I'll just send this through. Okay, so this pretty much is everything you need to know, including a bit of level 2, because the exam conditions say they assume you know the level 2. So remember this addition polymers, that I said you don't have to know at level 3 directly, but they could ask you for a comparison. So that's like your polystyrene. Okay. Your other polymers, okay, it sort of comes, yeah, it doesn't really show the polymers, but the formation of the amides and formation of the esters is like your polymer, because it's like making lots of connected esters or making lots of connected amides. Okay, but otherwise these are pretty much, remember your tests with Fehling's solution or Benedict's. Okay, you could also add onto here Tollens. Remember that's that silver mirror test. That aldehydes, because remember aldehydes gets oxidized by dichromate, permanganate. So if there's a color change there, you know something's happened. You can see here's a dichromate. Permanganate, the decolorization of permanganate, or if you are reacting it with that copper 2 plus ion, it forms that copper 1 plus red precipitate, or the other one is a silver mirror, the Ag being reduced to, sorry, the Ag plus ion being reduced to Ag, so making that silver mirror. Okay, so I know there's a heck of a lot on here, and that's why I say learn a reaction a week sort of thing, or you know, don't try and learn it too fast because then you'll get confused. Make sure you've really understood one reaction before you move on to the next one. So let's look at how we can do reaction schemes. So learn reactions by reactants. So if I've got an alkene, what sort of reactions can it undergo? And remember we did that hydration, hydrolysis, hydrohalogenation and hydrogenation sort of thing. And it can, and then those two tests. So you can learn it by reactant. You know, the starting materials. Or you could learn it by products. So if I've got an alkene, if I want to make an alkene, how do I make an alkene from a alcohol? Or how do I make an alkene from a haloalkane? So those sort of things. So learn it in reverse, if you like. And then learn it by reagent. So if I have got SOCl2, there's two cases where we use that. It's when we're turning an alcohol into a haloalkane, or if we're turning a carboxylic acid into an acyl chloride. So, you know, just try and use, you know, see where does every reagent come up? Do I have it in different reactions, or does it only come up in one reaction? Okay, then it's very helpful if you know your tests, because often that they add that to a reaction scheme and that gives you an extra clue. So if it says that it forms compound C, which decolorizes bromine, then you know you've got an alkene. So even if you didn't know what else it was, you knew you formed an alkene. Or if it said, and it formed compound C, which had, you know, tested positive with Tollens reagent or formed a silver mirror, then you know you've got an aldehyde. So if you know your tests, it's helpful. And then also know your Markovnikov and Zaitsev rules, because they could say, and compound C is formed, which is the minor product. So you need to be able to go, okay, I've formed, it's obviously either an addition reaction or an elimination reaction. Remember, addition is Markovnikov and elimination is Zaitsev. So which one is it going to be? Remember that rich gets richer and poor gets poorer as a memory aid. Okay, so let's look at some past exam papers. I think that's the easiest way. So they've said here, complete the reaction scheme by drawing the structural formulae of the organic compounds B and C. So they don't give you a very complicated reaction scheme. It's normally just a few reactions. Include any necessary conditions, okay? And they tell you compound C is a base. Now that you should immediately have a trigger for that. What basic compounds do you know? Organic, of course. And amine. Okay, Caleb, you're thinking of NH3, but when they say compound C, it's always talking about the organic. We don't consider the inorganics as such. So we know compound C has to be a base. Okay. So we have to go from propanol to a base over here. We know this is an amine. Now it could be a secondary amine, okay? And we know we're forming something which we react with a primary amine, methanamine. So that's a primary amine. Can you remember what reacts with a primary amine? As I say, there is a scheme. If I go back over here, page 78, you can also use that one. The haloalkane, correct? The haloalkane. It can be a secondary haloalkane, John. It doesn't have to be a primary one, but a haloalkane. So we know we've got to have a haloalkane there, and then we have an amine here. And it'll be a secondary amine, but it'll still be basic. Only the tertiary amines aren't basic. How do I change an alcohol to a haloalkane? SOCl2. Okay? So, as I say, read through all this, underline any clues. So this could be the tests, or here it's told you a property, it's a base. So you know you're getting to an amine, okay? And you know that you've only really one reaction that reacts with primary amines, and so we just put it all in, and there's your answer. So this one is still basic because it still has its lone pair. Okay, not that bad. Or what do you think? Do you think it's still? Okay, okay. Now, do you see you would have been stuck if you hadn't read all the way through and realized this has to be a base? Okay, so make sure you read everything through. So M's, yeah, that's what I say. It's not. You've just got to make sure you go through it. Okay, now this is a bit of a longer reaction scheme. This is from 2014. Okay, yep. So the primary amines and the secondary amines. And look, I mean, I teach this every year, and sometimes I forget the reactions. So, just keep on learning them, keep them in your mind, and if you've done level 2 organic, it's not so bad because you're just refreshing your mind for quite a few of them. And if you're doing level 3 without level 2, then it's quite a bit more learning. So here they told you all this information. Okay, A is oxidized to form product C. That's actually another way you can learn reactions, is actually by the reaction type. Is it an oxidation, addition, elimination? I know I'm trying to get my husband to make a Tetris type of game so that you can, as reactions come down, you can slot them into the different boxes, but it'll eventually get done. Okay, so we know there's an oxidation, so it could be an alkene to a diol, it could be an alcohol to an aldehyde, it could be an alcohol to a carboxylic acid, or an aldehyde to a carboxylic acid. That's where we come with the oxidation. And then there's another oxidation here. Then we've got SOCl2, and we know that comes up in 2 different places, alcohol to haloalkane or carboxylic acid to acyl chloride. Then I react it with alcohol B, and it forms an ester. Now that should tell you that this E is an acyl chloride, because I need the carboxyl type group, the carbonyl group, to make an ester. Okay, so that's already giving you clues. Then if D is reacted with an alcohol, it also forms an ester. And we know that H is an isomer of G, so it must be the same molecular formula, but different structures. And if I react with alcoholic ammonia, okay, I'm forming an amine with alcoholic ammonia. And when E is reacted with water, it forms product D. Now there's only one thing that reacts with water, and that's an acyl chloride. So you know product E has to be an acyl chloride. You get given the clue there, okay, and you get given the clue here. So you know this product E over here has to be an acyl chloride. So let's go through. We've got propene, and we're forming a major product or a minor product. So if it's a major product, the hydrogen adds to the end carbon, okay, and what adds, what are we going to form over here? So in other words, are we going to form propane 1-ol or propane 2-ol? The secondary alcohol. Okay, yep, so the 2-ol, because it's the major product. So the hydrogen is going to attack, you know, the rich gets richer. So if you think of I should actually, I wonder if I've got you. Oh, okay, I've said the product C is a ketone. Why did I say that? Oh, okay, it has to be a ketone if this is going to be a secondary alcohol. And then this must be a primary alcohol to form the aldehyde, perhaps carboxylic acid. Okay, this has to be an acyl chloride because we've got those tips over there. And if I'm reacting it with ammonia, it's a nitrogen I'm adding on, so I've got to have an amide of some sort, either an amine or an amide, depending. Okay, so here's propene. So remember, the rich gets richer, so the hydrogen adds onto this carbon, which means the OH has to add onto that carbon to be the major product. Okay, and the minor product is the other way around. So the OH will add to this one, and the H will add to that one. Then oxidation, ketone, here oxidation. Now, why did I choose the carboxylic acid and not the aldehyde? Will an aldehyde react with SOCl2? Yep, okay. So it could become an acyl chloride. So an aldehyde, you know, you've only really learnt the oxidation of an aldehyde or the reduction of an aldehyde. They do other things, but you don't have to learn it. So I have to have formed the acid to form the acyl chloride. So there it is. And then what basically happens, the Cl gets kicked off, and the more basic NH, well, the ammonia adds on as an amine. So I formed an amide. Okay, carrying on over here. This is, remember, we're taking product D and we're reacting it with alcohol B. So remember, alcohol B was the primary one. So what we're doing is, this is now the purple bit here. So the O of the alcohol adds on, and we've got H2O being kicked out. The OH over here plus the H from the alcohol gets kicked out, and there's my ester. And to make the other ester is when I react it with the secondary alcohol. So can you see there was product D, and now there is product A that's added on. Not too bad. So you always get sort of given some sort of scheme, but you are given tips. So here they didn't really give many tests or so on, but they did, you know, say it was an isomer, so you knew that these two had to be the same thing. And you just got to go, you know, you're told minor product, major product. So Caleb, you've got the what language? Oh, and this actually is, sorry, it's a whole, so we've finished there, and we've got a little bit of extra time. Oh, Afrikaans. Oh, there. Oh, yeah, what is, yeah, okay, I see there is. Yeah, or German, yeah. Yeah, Afrikaans, yeah, German. Okay, this was last year's exam. So if we, in the last few minutes, go through it, if we wanted to do this, and I'm just trying to find my, there, sorry, I've just got to find it there, okay, and I need to I don't want to delete pages, sorry. I know what was happening. My tablet that I was using, I had upside down, so I was moving my pen in one direction and my cursor was going in the other direction. So I was getting very confused. Okay, so here they give you aspartame and they basically ask you for functional groups. So what is this functional group, number 1? Carboxylic acid. Okay, what is number 2? An amine, correct. What is number 3? An amide. Now it is an amide. It's a secondary amide. It's an amide, but it's still an amide. I don't know if they would accept if you said peptide link. They may have, okay, because it is also peptide link, but as a functional group, it's still an amide. And then what is this one over here? Okay, here. That's an ester. Okay, so that's a sort of straightforward achieved level introduction to make you feel a bit better. Now this is, they've got to draw, you've got to draw the compound. So what I want you to emphasize is if I drew it like this, I promise you I will not get any marks whatsoever. Why won't I get anything? No H's. They very insistent that you have to have H's. When you get to university, you know, all you have to do is do that, and it would be totally accepted because every sort of junction is a carbon, and you know it's what we call the skeleton equation, or you know, for organic compound. But for so I'm just going to delete that. For level 3, you have to draw your you know, all the hydrogens. Now for this one, remember, I'm going to just draw something and I want you to tell me if it is correct, assuming all the hydrogens. I'm lazy. Let me put them in. Is that correct? A carbon is missing. Okay, pent means 5, so count your carbon atoms. Okay, butanol is, particularly if you're naming it or even if you're reading it, please read very carefully between the L and the O, because I find students often misread, or their writing is so untidy. If they were naming it, it doesn't come out very clearly. And I know if, so I'm just trying to find the delete button there. Okay, for a bit of toilet humor, that's but anal, if you want to try and remember butanol. But that's just some toilet humor. Okay, right. Now this is where you've got to draw your structural isomers. As I said to another student I saw yesterday, you won't ever be asked to write all the organic isomers of a particular formula. But they can give you a molecular formula and tell you to do a particular type. So they could say, draw, as they did in this case, a primary haloalkane, secondary one, a tertiary one. Or they could say, draw a branched secondary, or something like that. Or they could say, draw 2 compounds, one of which is an optical isomer and the other one is not. Or draw 2 which have got different functional groups. Now obviously this one will only allow you to have one functional group, okay, because it's Cl. But once you have, say, if you had C4H8 O2, for instance, then you can have alkene and OH in the compound, or you could have an aldehyde, or you could have a ketone, or you could have a carboxylic acid, or you could have an ester. So if they say, draw something where the functional group is different in each case, you must make sure you have different functional groups. So in branch, just make the chain skew. So here, if I said draw a branched isomer of this, then you've got 4 carbons. If I did 4 carbons in a row, that's straight chain. If I did 3 carbons in a row and I made a side chain, is that what you mean by skew, April? It doesn't matter where the chlorine is. If I just said draw a branch chain and a straight chain, I could have made the chlorine anywhere over here. To fulfill the requirement, draw a straight chain haloalkane, draw a branch chain haloalkane. So that would be correct in each case. But if I ask for a tertiary haloalkane, then I've got to have the Cl over there. Right, I did want to sort of go down more to, okay, here they're asking for KOH and alcohol, identification of all organic products formed. Now, tip here, when you see something like this, if you're going to form an alkene, you think of Zaitsev, okay? So you think of major and minor, but please also think of cis and trans. If you're going to form an alkene that can form geometric isomers, mention those as well. So don't just think of major and minor product. Okay, so they give you lots of space, so they know that you've got to do lots of writing. Okay. Here, okay, they're talking about optical isomers. Right, and they ask you always how to distinguish it. When you're asking to distinguish between the enantiomers, remember it's rotating the plane of polarized light by the same amount in different directions. Don't just say, well, you could say rotate the plane of light, but it's better to say polarize, because you have to polarize the light first, and then that plane gets rotated. So don't just say it rotates light. You won't get anything for that. So it's got to rotate the plane of polarized light the same amount but in different directions. Okay, as a matter of interest, if I have equal amounts of enantiomers, okay, will it rotate the plane of polarized light? No. Remember that racemic mixture that we call it? A racemic mixture does not, because the one enantiomer is trying to rotate it to the left and the other one is rotating it to the right, and so eventually nothing happens. And remember, with your 3D structures, please don't draw something like that just because you had, OH here and you're trying to do the mirror image. Sorry, that's supposed to be an O. Don't make hydrogen have 2 bonds. Hydrogen must have 1 bond only. Okay. Okay, there's you are going to get a polymer question. So that's just the polymers. Right, that's still polymers. There was a lot on polymers last year. Okay, this is important. Okay, I see it's nearly time, but it is important that you look at those videos so you can get an idea of the type of equipment, because there is invariably a question asked about equipment. So you can't carry it out, unfortunately, because you're doing it by correspondence. So have an idea of, okay, triglyceride, that is, they explain it here. So a triglyceride is just simply an ester. So this is your fat, okay? So can you see it's an ester, and it's tri because there's 3 of them, and this is the fats that occur in your body. You have this particular compound that is bonded to 3 fatty acids. I don't know if you've heard the term fatty acid before. It's just simply a carboxylic acid that's got a very long chain. These are all very, very long chains. So they dissolve in fats. Okay. And okay, there's an example. So can you see that's a sort of reaction scheme you've got? Now here they haven't given any identifying tests. So they haven't sort of said test positive for tolerance or anything like that. But they have given you clues down the track. So to get from there to there, it should be easy enough to work out the middle bit.